So yeah, Camille is in the main shared screen. It's correctly settled. Okay, so just checking time. I guess it's a good time to resume. So hi again, everyone. And for this second talk of the session, we have the pleasure to have Camille Male from Bordeaux, who will talk about some computational aspects of free convolution. So we are listening to your talk.
Thank you very much, and thank you for the invitation. So that's a great pleasure to introduce this setting. I will talk about some computational aspects of the free convolution that has been introduced by Guillaume in the previous talk. And I will address this question in a more general problem. So let me first explain the very general idea, and then I will introduce the plan of the talk. The problem we want to address is to find this one, it's going to be better, is the following. Assume we are given a Hermitian matrix, the Hermitian random matrix, that we assume to have the following form. We have a matrix Hn as Hermitian that we write as a polynomial in several matrices. So we assume that P is a polynomial or a rational function in these matrices, but it will be a non-commutative polynomial. Non-commutative because as it involves the product of matrices, the order of the matrices matters. We assume that this guy is fixed when n varies. And we assume that the matrices A1n, A2n, up to ALn are independent random matrices. And the question we want to tackle is to understand the spectrum of this matrix Hn in terms of the model. Of the models for the independent matrices ALn. So these are the ingredients, and you want to understand how this complicated operation, it will result in a spectrum and how to compute it. And so, of course, the first example that we can have in mind is the example of a sum of two matrices. And we can think that we have one guy which is deterministic, for instance, and which is the signal, and one guy here which is random and which is like a noise. And in this specific example, we wonder what will be the influence of the noise in the spectrum of AN. And if it looks a priori as a very specific problem from this general question, it turns out that solving this question can be is possibly done by solving first just the question of the sum of two matrices, and some techniques of free probability and non-commutative probability allows you to reduce this big problem to just this one. This is why along the talk I will talk only about the question of the sum of two matrices and talk about different notions of convolutions. But at the end, there is a machinery that allows you to solve the problem for an arbitrary polynomial. Okay, so let me just give a definition. We call empirical eigenvalues distribution of the matrix AN the probability measure that I call L index AN, which is 1 over n, the sum of the Dirac mass in the eigenvalue. So lambda I of AN is the eigenvalue of the matrix AN. Okay? And so we have encoded the spectrum in a probability measure. And what we are looking for is the behavior of this probability measure for AN, or the L of the sum of two matrices AN plus BN. So here is the organization of the talk. I will first talk about a result by Pasteur, which is about one case where for the random model, we have specified a matrix with IID entries. And then I will talk about the notion of free probability, and we will see the free convolution in its general setting. By Voiculescu. And then in the third part, I will present extension of these two results. Because these two results will be about some class of universality, which is not very general, even if there are a lot of classical results in this setting. And then we will see an extension for a much more general situation where we have random matrices of different kind of symmetries. Okay? And there are three parts, but these three parts, I will look at different situations where a single equation, which is Pasteur equation, that will become Voiculescu extension and another extension. And we have a single equation that rules the spectrum of the sum. And we will see how we can visit this equation several times in more and more general situations. So I will start with this Pasteur equation, the original one. So to introduce this equation, I will define the matrix model with independent entries that I want to consider. And because the matrices are Hermitian, when I say independent entries, I will specify something very precise. I call a Vigner matrix is a Hermitian matrix so xn is equal to xn star, and I assume that its entries are written in the following form. We have random variables, xij, which are divided by square root of n. We have this normalization. So typically, we have a lot of random variables of small amplitude. And we assume the following. The xaj I will consider the real model, so they are, so let's say, a real symmetric. They are IID. So the entries which are in the smaller triangle, xij. And they are distributed according to some distribution pi, which is independent of n. And in the context of this talk, we'll assume that these entries are centered and they have finite moment of all orders. So this is typically a matrix of noise, and it just fulfills the Hermitian or self-adjoint symmetry. Okay? So we have a theorem which is due to Vigner from the very beginning of the theory of random matrix, which tells that the empirical eigenvalue distribution, so this guy, converges almost surely and in probability to the semicircular distribution. This means that if you do an histogram of the eigenvalue of this matrix that you can sample here only by choosing the common law of the entries pi, you will see that this histogram is very close to the semicircle. Okay. So this is just about the behavior of a single matrix. And so the question that we consider, and that is solved by Pasteur, is to consider the sum of these two matrices here, where we assume that AN is a Hermitian matrix, or XN is a Vigner matrix, and AN satisfies that the empirical eigenvalue distribution of AN converges to some measure that we will call mu. And let me call mu this semicircular distribution. So a theorem which is due to Voiculescu, which is a consequence of his main result in 91 in the connection between free probability and random matrices, is that the empirical distribution of this sum, AN plus XN, converge to the free convolution of the measure mu and mu. And the question that I want to address more specifically is how to compute it. Of course, if AN is a zero matrix, we know that we have 0 here, and it's just the semicircular distribution. But what is this object and how to compute it? And then, when Xn is not a Vigner matrix, but something more general, what will be the machinery to compute the distribution of the sum of the two matrices? So, to give you an answer for this, I will introduce a tool which is called the Stieltjes transform. The Stieltjes transform of a matrix, let's call it a generic matrix AN, is the map that I'll call G index AN, which take lambda, which is a complex scalar which is not in the spectrum of AN and associate the normalized trace, the trace divided by the dimension of what we call the resolvent of AN, which is lambda times the identity matrix minus AN to the power minus 1. And this guy is called the resolvent. And this tool is very interesting for us in the context of random matrices. So let me first explain why, when we know the Stieltjes transform of the matrix, we know the spectrum. And when we will have this tool, we will see how to write equation on this object. But first, we must know how to connect this transform with the spectrum of the matrix. So we have this fact. If AN is Hermitian, then if you look at the empirical eigenvalue distribution of AN and want to compute it on an interval, let's say of the form AB, an open interval like this, you have a formula. It is assume that, let me assume for simplicity that there is no atom. Then this guy is just a limit when a small parameter converges to 0 of minus 1 over pi, so the integral of the imaginary part of the Stieltjes transform of AN in X plus E epsilon. So for an Hermitian matrix, the eigenvalues are located on the real line. And if you want to understand what is the distribution of eigenvalue, what is an approximation of this histogram, what you do is you consider a small parameter epsilon, and as X varies, you compute the Stieltjes transform at this point. And if you know how to compute the Stieltjes transform on this part of the spectrum, close to the real axis, but at some bounded distance, then you will be able to understand the eigenvalue distribution. And in practice, it works very well. When you do, you know that, you know the numerical values of this guy, you will be able to compute the density of this empirical eigenvalue distribution. Okay, so let us state the theorem by Pasteur. So which holds in this setting. Then the empirical eigenvalue distribution of the sum of two matrices converge to a distribution that I call L index little a plus little x, but just a notation to remember that it is a limit of the distribution of the sum, given by the following. If I consider the Stieltjes transform of this sum, a plus x, so this is the Stieltjes transform of this measure. It satisfies the following fixed point equation. The Stieltjes transform of the sum equals the Stieltjes transform of this limiting Stiegler's transform of this deterministic matrix A applied to lambda minus the Stiegler's transform of the sum. Here it is. And what is important about this is that it gives us a fixed point equation for the quantity of interest, which is the Stiegler's transform of the sum. Meaning that if you know well enough the distribution of eigenvalue of an, and you have a proposal for its Stiegler's transform, you are able to compute this ingredient. Then you can plug a fixed point method just by initializing this guy and applying many times this equation in order to get a numerical approximation of this Stiegler's transform of the sum. And you evaluate this for a parameter lambda, which is in this fact close to the real axe, and then you will be able, in practice, to compute the Stiegler's transform of this value, and hence to have a nice approximation of the density. So this is Pastor equation. And if you're okay and everything is clear, I will continue addressing a new general problem. More general problem. And this Pastor equation becomes the subordination property in the context of Tulescu. So now I will address the problem of computing what is really the free convolution, but in a general setting. In this setting, it is the sum of an arbitrary matrix with a Vigner matrix, which means that the limiting distribution of this guy is a semicircular distribution. And this guy here is actually the free convolution of the limiting distribution of an with the semicircular distribution. But now we are considering a more general setting where we have the free convolution of arbitrary real distribution. So we consider now the sum of two matrices Bn, where I will assume that An and Bn are independent random matrices. I assume that the empirical distribution of An converges to some distribution, and I will call it L of A as a notation, just to remember that it is a limit of An. I call the limiting distribution of Bn L of B. And I assume that one of the matrices, let's say Bn, that Bn is unitarily invariant. It is equal in distribution to the matrix UB U minus 1 for all U unitary. And so I address the question, what is the empirical eigenvalue, the limiting empirical eigenvalue distribution of Hn? And I will call to start the setting for this theorem. So as before, as said in the talk of Guillaume, the limiting distribution of Hn, so An plus Bn, is the free convolution of the two limiting distribution. The question as before is how to compute this distribution in practice. So I will introduce another material, which is which comes with the Stiegler's transform. The R transform of a probability measure mu is the unique solution of the following equation, which tells you that the Stiegler's transform of your measure mu satisfies this equation. So
before U was random unitary. Yes. Random. Okay.
So if it is an equality in distribution between two random matrices. So I write it as an equality for deterministic matrices U, but it means that U equals this guy when U is random and it is distributed according to the R distribution of the unitary group. So if it is, if you prefer, you can write it as an equality with a random matrix. But it's correct like this also. Okay? Cool. Okay, so let's look at this definition of R transform. It is a fixed point equation as we have here, but now we don't plug something outside here. It's just the inverse, but we have a function here which modifies the fixed point equation. And this R mu is defined in an implicit way, which is not always very convenient, but it is uniquely defined when lambda is in a good domain of the convex plane. And then we can state Voiculescu's equation. And again, it is consequence of his work in '91 because all the technology about subordination was discovered before the connection of certain matrices. In the second setting, the distribution of the sum of two matrices converges to this measure, which is a free convolution. And now, what we have to integrate here is the role of B, which is no longer a semicircular distribution. Now we have this R of B apply in G of A plus B in lambda. So the new ingredient that we add is that here we put the R transform of. And the second consequence is that if you want to understand this free convolution, assume that you can compute easily from A the Stieltjes transform. If you give me some complex number, I will compute G A of lambda. And on the other hand, from this variable B, you are able to compute the R transform. It may be tricky because the definition is implicit, but if you can do that, you have this very nice fixed point equation where you can get what you want, the quantity of interest, which is the Stieltjes transform of the sum. And RB is linear, means that this equation is Pasteur equation, is equivalent with the fact that the empirical eigenvalue distribution of the matrix Bn converges to the semicircular distribution. But out of the semicircular case, when it's not just the specific case of Vigner matrices plus a deterministic matrix, you have the free convolution in general, and the equation is just a variation of Pasteur equation. Okay. So if this is clear, I will go to the third part when we are going to consider a more general model. So as before, I will consider this setting. But I will relax the unitary invariance assumption. I will consider this third setting where I have independent matrices such that the empirical distribution of one matrix converge, of the second matrix converge, and I will give two definitions about the kind of example we want to generalize. First, we consider a Vigner matrix with a variance profile. So it's a matrix that I call XM, which is Hermitian. And I assume that its entries are as a Vigner matrix as before. But now we have some weight on each entry, such that the weightless matrix is a Vigner matrix. And the matrix gamma AJ defines some different variants for the entries. We assume that, so this is self-adjoint. And let's say that it is bounded, each entry is bounded, let's say, by 1. Okay? So if we have positive number here, they act as variants for the entries here. So this is the first kind of generalization I want to consider. And the second kind is about, so this relaxes the model of Vigner matrices. The other assumption relaxes the unitarily invariance. We say that a random matrix Bn is permutation invariant if and if Bn equals in distribution to Vn transpose for all permutation matrix Vn. Okay. And so we will consider the case where the matrices are independent and Bn is either a matrix of the Vigner model with variance profile or a permutation invariant matrix. So in this case, assuming that we have only the convergence of the empirical eigenvalue distribution of An and Bn is not very a good assumption, because the spectrum of the sum in this general setting will depend on more than the distribution only on the eigenvalues. They will depend on the position of eigenvectors. When the matrices are unitarily invariant, or one matrix is unitarily invariant, the relative position of the eigenvector of An and the eigenvector of Bn is arbitrary and is in generic position. But if we only work under this permutation invariant assumption, or that we break the symmetry of the model with a variance profile, it is no longer true that this will only depend on this. The consequence is that we cannot expect to have a theorem where the distribution of the sum in the limit is simply a function of the distribution of A and the distribution of B. But there is an extension of this equation which works very well and involves only few new ingredients. I will introduce these ingredients right there. So I introduce for a matrix An, the operator G of An of lambda, which is somehow an extension of the Stieltjes transform, and I denote it like this. And there are two symbols that I must define here, which is the symbol delta and the symbol lambda. So delta is what I call the diagonal operator, which takes a matrix, let's say a generic matrix Bn, and gives us the diagonal matrix of the diagonal element of Bn. And lambda is a diagonal matrix. So I will call in this ensemble diagon of C, such that the imaginary part of lambda is a positive matrix, which means that its diagonal entries are strictly positive. Okay, so it is a variation of the Stiegler's transform, and what we did is that we replace the resolvent by something a bit more general, because this diagonal matrix is not necessarily a scalar matrix. And moreover, here we had before the normalized trace, so that we get a complex number, but now we only take the diagonal of this generalized resolvent. And then this guy is also a diagonal matrix. Okay. Similarly, we define an extension of the R transform that I will denote Rn as before, such that the diagonal of the generalized resolvent is lambda minus this new R transform in the diagonal of the resolvent. So it's the same fixed point equation, but now I have only changed the nature of the object which are involved. So it is another functional. It is somehow more general because it takes more general objects. So in the context of 3, of the sum of two matrices where we have either this permutation invariant symmetry, either a variance profile for a Vigner matrix, and we can also allow to have a variance profile and permutation matrices in a more general version, but let's talk about this. And so this is in the paper mentioned by Guillaume, by O, Sebron, Dalglist, Gabriel, and myself, is that the empirical eigenvalue distribution of the sum is given when n is large by some approximation, and I will be a bit less precise in this context. This map big G of an plus bn, so this generalized Stiegler's transform, satisfies up to a small error the fixed point equation that we introduced before, but with some different symbols inside. The equation is the same. So here we recognize a Voiculescu subordination equation, but here it's not longer the Stiegler's transform, but this functional, which is solution of the fixed point. The ingredient in the matrix AN we consider in this equation is the general Stiegler's transform. And here, the ingredient we know, or we assume to know in Bn, is the generalized R transform defined as solution of this. And numerically, it works very well if you want to have an approximation of this object, to just assume that you have this fixed-point equation and to look at its unique solution. And at the end, if you want to understand the spectrum of the sum of two matrices, you know that it is enough to understand the Stieltjes transform. But to understand the Stieltjes transform, if you know this more general functional, you just have to evaluate 1/n the trace of this generalized Stieltjes transform in the parameter, which is a scalar, lambda times the identity. So, thanks to this equation, you are going to get this object, and then with this simple formula to understand the Stieltjes transform, and as explained before, knowing the Stieltjes transform, you will get an approximation of the density. So this is almost the end of my talk. So let me just give a remark. So before, in 1 and 2, we had a fixed point equation for the Stieltjes transform of an plus bn, which was true in the limit. So I write it as for the limit as an equality. And this thing belongs to the set of complex numbers. In 3, as you mentioned, I'm less precise. I just use this symbol because I have a fixed point equation which is true in the limit in some sense for the generalized Stieltjes transform. But note this guy is a diagonal matrix of size n, which means that at the question of numerics, you have an object which is more complicated to involve. On question of giving a formal definition of the limit, it's a bit tricky because here you have an object which depends on n, which means that this equation should be written with some care in the limit when n goes to infinity. But in the first case, there exists a quantitative estimate of the error we made with this equation, but in this context, we don't have such a quantitative estimate, so it remains an open problem to write it. So I think that it's the end of my talk, so I thank you very much, and I'm open for your questions.
Well, thank you very much for your talk, so we can applause first, and then we can talk. And okay, so if you have questions, feel free to ask them either in the chat or to unmute yourself or raise hand, whichever way you prefer.
So I see a question by yourself, Sebastian, right? Is AN still deterministic? So at some point, I choose to consider AN deterministic for the storytelling. Deterministic plus noise, but at some point what is important is that these two possibly random matrices are independent, but you don't care about one is deterministic or not.
Yeah, sure. So I don't see you anymore, but I don't know if it's the case of everyone or just me. Anyway, are there so there is a question, Andre, you can.
Thank you. The question, thank you for a great presentation. Related to the matrix Bn, you limited it to a Vigner matrix with a variance profile and the permutation invariant. Would this work also in other cases? Would you possibly have some problems with the fixed point? Why is this limited only to these cases? Is it possible to extend more broad? Thanks.
It is possible to extend indeed. For instance, you can take Bn, which is, you take a variance profile on a matrix that I call Cnaj, where Cn is permutation invariant. So this is combining the two ingredients that I have for simplicity separated. Another example is you take a matrix which looks like a Vigner matrix. Let's say I don't need to, just to give one example. You take the same symmetry of independence as a Vigner matrix, but for the distribution of the entry, you take a Bernoulli random variable with parameter P over N, where P is fixed. Which means that you have a matrix of noise, but which is not made of a small noise, which fluctuate on every entries. But because you use Bernoulli random variables, on each row, in average, you have a finite number P of entries which are non-zero. So it is a very sparse matrix. So it is quite different from a matrix with a variance profile. It actually turns out to be a permutation invariant matrix, but it gives you maybe a more concrete example. And we expect that this phenomenon is called freeness with amalgamation over the diagonal. This is the language in free probability. And we expect that it is true in more in other examples, but this is for the moment the class of matrices that we have investigated.
And are there also cases where this doesn't work? Where this wouldn't work?
Yes, if you take matrices which are very dependent, but I mean, I don't know so much examples of random and natural model for which when you consider the sum, you cannot consider this kind of equation to solve the spectrum. But maybe because I'm always focusing on these examples which works.
Okay, thanks. Thanks a lot.
Welcome.
Sorry, can't you return to some fact? You say that if A and B are not the atoms, then some identity is valid. But what is valid for any n or in the limit?
Sorry, again, what's the question?
There was some identity that something is equal to something, then A and B are not atoms. But
yes.
This identity was valid for any fixed n or on the limit?
It's true for a Stieltjes transform. And so we use it in the limit in practice, but it's true for in general.
Can you write it once more? Something
in general, you have a measure mu. We have the Stieltjes transform.
Integral, something integral, yes.
Exactly. And we have, there exists a reconstruction formula. By reconstruction formula, I mean, which gives you the measure in terms of the measure mu. And then you can apply this fact to reconstruct the empirical eigenvalue distribution of your finite size matrix in terms of the Stieltjes transform of your matrix for finite size. But what I was explaining is more about recovering the limiting distribution in terms of a limiting object GA, because this is this GA which is really the solution of the fixed point equation.
It was
there is no limitation.
Identity. Someone mentioned identity that A and B are not the atoms of some measure, I think.
No. Sorry about
valid,
the confusion. A and B in my talk were limit of random matrices, but they are not related to the A and B I was using in the facts about the atoms. I should have used other symbols.
So
I asked a simple question. This identity about two values, it was fixed for any fixed n, or it is some limit. It's strange. There's integral. There was integral of imaginary part of something.
I can write it again if you want. But it's not related to finite size matrices. It's true for any probability measure and its digest transform. And let me write it with the good symbol is mu. And let me write without assuming that we have no atoms, but I will use two other symbols, X and Y. 1/2 of the measure of the atoms that did not appear before, minus the limit of this integral of the imaginary part of G mu in X plus E epsilon, right? Dx. Okay?
Yes.
And if you let X converge to Y and there is no atom, you have a formula for the density in a point X when the density exists. Just remove the integral.
Thank you.
Okay? And so this is true if you want to compute L of A from G of A, but this is also true if you want to compute L of AN from G of AN. Just
for any n? Or in the limit?
Yeah, it's true. It's true for any n. It's true. But in the story that I told today, what we get at some point is this distribution GA, because it's only on the limit that we have the fixed point equation. This is when S goes to infinity. Remember, with the small symbol G, we have an equality. So this is in the context of this story about the limits that we use this inversion formula. But if you want to use this formula for any n, it is true.
Thank you.
But voilà.
Thank you.
Are there other questions? If not, maybe I have one or two, or just one slight comment, because I don't know how much it is used out of France or not. The XY interval with inverted bracket, it's the open interval. So maybe people know it with parentheses, the mu of XY. I don't know to which extent it's used or not in non-French math. I don't know if it was confusing or not, but I just say it in case. So thanks a lot for the talk. It was really cool. I had one question. Is it possible to explain to non-specialists somehow the kind of techniques to compute R transforms? Is it understandable, or it's?
It's very difficult. I mean, I don't know how to compute a lot of R transforms. And so there is this case, did I mention it? I did not mention, and I forget this. These matrices with variance profile were studied first by Schlecht and Co. And Schlecht and Co computed this complicated object in this case. For a Vigner matrix with variance profile. What is complicated is that this definition is implicit. So you don't have a way to tackle the question where Rn of An equals something patati patata. No. So what you can do is to try to obtain this equation. And so you take the diagonal of the resolvent of your matrix, lambda minus your variance profile matrix, let's say it's X minus 1. And you want to write it as and to introduce some equation to get something. Remember, this is the diagonal of the resolvent. And there is a formula which is called the Schur formula, which gives you, when you have a block decomposition of a matrix, if you have let's say, okay, let's call M this matrix. So you have some matrices here. And it gives you a formula for the inverse of the matrices. And here you have combinations of these matrices here. And one typical method when you deal with Vigner matrices where you have independence is to use this Schur formula because this is very similar to the matrix you considered before. If it's a Vigner matrix, this is a Vigner matrix. If it's a variance profile Vigner matrix, as well, this is a variance profile Vigner matrix. So if I want to give you one ingredient, one clue to do computation about this diagonal of resolvent or Stieltjes transform, this is this formula, which gives you the entries, the block decomposition of the inverse of a matrix. And then you use concentration, and you need to understand how these things behave to understand that this R transform, R of AN, will be a linear map, but a linear map from the diagonal matrices to the diagonal matrices. And Sheck and Co. exhibit what is this linear map in the case of a variance profile. Maybe I'm not giving exactly the formula, but it's quite simple. It is a linear map, so it is just a matrix which explains what is this degree of linearity. It's a variance profile which acts as a diagonal matrix.
Okay, thanks a lot. I had also another question, maybe about what you said last in your talk about like in the third section, you have an almost equality, like when n goes to infinity, but it's a bit subtle because the space is evolving with n. I was wondering, like, could like formalism such as Feynman algebras or free probability stuff, like, could it help to make them live in the same world, or is it?
It does, because Vigner created 40 years ago all the framework, so it's possible. In the framework of classical non-commutative probability, when you have the set of random matrices and the normalized trace, this is just seen in a limiting way as an algebra, let's say a Feynman algebra, on phi, which is a state on A, or a linear map. But in the case that we are considering here, we have one more ingredient, which is delta. And the scalar are replaced by the diagonal matrices. Well, in this algebraic setting, Vigner proposed to consider this setting, but equipped with delta, a linear map valued in an intermediate algebra B, where this guy is called the conditional expectation. And Vigner define what means freeness with amalgamation over the algebra B, which means the conditional in the analog of conditional independence. What is the good algebraic structure we must consider, and what is the formula for freeness over the algebra B, which gives you an identity in this context, not something like this symbol, but an identity for the analog of the diagonal of the resolvent, but which is well formulated in this setting. So there is something very precise there. What you want to say is what is the convergence in this setting. It's just technical, but the framework exists and is very well defined.
Okay, thanks a lot. Is there a last question or not? We already have had plenty anyway. Okay, so I propose we have a last round of applause to thank the speakers again.
Thank you very much. Thank you, Guillaume. And thanks the organizers.
Of course. And just a last word, and then just to say that in 2 weeks, so on February 3rd, there will be a session with Russell Lyons and Jason Berstock about probability intersecting the realm of Coxeter groups. So